All right, so we're going to carry on with chapter 8. Right now, we're specifically looking at section 8.4, which is our discussion about what's called trigonomic substitution. And what is this all about? Well, what we're trying to do is take integrals that have certain forms and convert them into a trig function, which makes it easier to take the integral. Okay, so in other words, sometimes we can take a very messy integral and rearrange it somewhat into something a little bit simpler so that it's easier to integrate it. And there will be a lot of that throughout this chapter. A lot of the trig functions are very useful in different forms. And so what starts to happen is after a while, we start to develop a talent for seeing how to take these horribly messy cases and turn them into something a little bit more down to earth. Now, that usually means there's a lot more steps involved, of course, but at least it's possible to find what we're looking for. So, anyway, so we're going to start with these three basic cases, which you can see here. All right. So if you run into one of these, you'll know to use trig substitution and you'll know how. Right. So here they are. Now keep in mind in these three cases, A is meant to be a constant, as has always been the case. This book always uses A as a constant, and then U is a function of X. Now they've repeated for us very helpfully the Pythagorean identities because we're going to need them quite a bit. Once you got our results from these substitutions, sometimes it's still not good enough. We need to do something to simplify it a little further. And often the way to do that is with one of these Pythagorean identities. Okay. Now we're very familiar with these. We've seen them before, but you never know when they might come in handy. Okay. Now they've written it as cosine squared equals 1 minus sine squared theta. You might recognize this as sine squared theta plus cosine squared theta equals 1. Of course, it's the same thing. And this in turn is derived from the Pythagorean theorem, which we all know very well. All right. It's one of those formulas that never escapes your memory. Um, if we let for a right triangle, the two sides are A and B, and of course, C is the hypotenuse. Yes, this is something you never forget. All right. Anyway, so let's take a look at an example of what we're supposed to do with these three cases. We'll start with radical a squared minus u squared. And what are we expected to do with that case? Well, what they're going to tell us to do is let u be replaced with a sine theta. Now, they're going to show us why with a diagram. So, in other words, remember that the sine of theta is the opposite over the hypotenuse, which means u over a. Um, which simply, if we cross multiply, implies that u is indeed a times sine theta. Okay, so we're going to use that to help simplify our results into something a little bit more manageable. All right, so let's look at the first example. Here we go. Now look at this thing. At first glance, you might say, this is a job for u substitution. Ah, if only. See, the problem is that if you try to use u substitution, you will not be able to find the du that you need. And so that's not going to work. So instead, we say to ourselves, wait a minute, this looks awfully familiar. It sure does. If you let a be a be 3, if a is squared is 9, then of course a is 3. And then U would be X. Okay. And so what else do we need to know? Well, let's take a look at this graph one more time. And remember, they did tell us that U should be replaced with A sine X. Okay. I'm sorry, not theta. Because, by the way, we are actually converting this integral into a function of theta first, and then we're going to replace all the thetas or bring them back to x's when we're done. So, in other words, we're changing the variable that we're using when we use this procedure. Um, we will replace the x's um, with equivalent functions of theta. Then we take the integral of with respect to theta, not with respect to x, and then we can make the necessary substitutions to bring it back to x. Because ultimately we want the answer to be a function of x, not theta. Okay. So to create a function of x. So that's in a nutshell what we're actually doing here. But the motivation is to simplify everything. Because right now, the way things stand, I don't think we can integrate this with respect to x. So we're changing the variables in the very convenient way, doing whatever we need to do, and then bringing it back to x. You see this all the time in math. It's not just for integration. If you've got a messy process, often you can turn it into something easier with a change of variables rather. And so this is one of those cases. So anyway, let's see how this is going to work. Now remember, 2a is 3. Sorry, 3 sine theta. And remember, we also noted that u is x. Oh, all right. Well, that helps. That means, of course, that x squared is 9 sine squared theta. It also means that dx is 3 cosine theta d theta. It also means that the square root, radical 9 minus x squared, minus x squared, which we just showed is 9 sine squared theta. Now, this one can be simplified even further. Now, you might say to yourself, well, how do I take the square root of this? You don't. But you go back to the Pythagorean identities and you say, hey, wait a minute. 1 minus sine squared theta equals cosine squared theta. That might be easier to take the square root of. And yes, it is. Oh my God. So, although it's hard to see because we're scrolling up and down all the time, we now have everything we need to make the necessary substitutions. Hold on one second. All right, so here we go. Let's go get this back. So we know, for example, that dx is from way up here somewhere, 3 cosine theta d theta. X squared is um, 9 sine squared theta. And this messy square root is actually nothing but 3 cosine theta. All right, now look how simple this becomes because you've got some cancellations. All right, now you're looking at this and saying, what do we do now? Well, here's what we have to remember. 1 over cosecant. They're inverses of each other, which implies that 1 over the sine squared of theta is the cosecant squared of theta. I can make that substitution. Now, if you look at the chart or the table, I'm not sure if it's open here. If you look in Brightspace, you'll see there's a folder for um, tables. I don't know if it's open or not. Hold on 1 second. Let's see if we can get that open. Yeah, I put these up here. I thought it might be convenient to have a lot of the useful tables listed here separately. Sometimes it's very helpful. The one we want is the rules of integration, basic rules of integration, not the massive multi-page table from the back of the book, but this one. And if you scroll through it, you're going to say, well, wait a minute, is there a rule here for um, the integral of cosecant squared? Okay, we need cosecant squared. We scroll down and, oh, wait, there it is. The cosecant squared u du is negative cotangent u plus c. Well, that's quite helpful. So let's do that. Now, you might think we're done, but the problem here is that this is a function of theta. We need a function of x. So let's go back and get our diagram and revisit this. Oh, God, sometimes this eraser just doesn't want to work. All right, I'll just grab the whole thing. Yeah, and every once in a while, it just randomly erases stuff. It's very frustrating. All right, I will just, I'll leave it alone. Anyway, so in other words, we've already seen that u is 3 sine theta, but it's also equal to x. And we also saw that the square root here, that was originally 9 minus radical x squared. So the theta, the tangent of theta is the opposite over the adjacent. The cotangent is adjacent over opposite, which in this case would be radical 9 minus x squared. The opposite is x. So we're almost there, but remember, we don't want the cotangent. We want negative 1/9 the cotangent. And we also need the c. All right, so after all the dust settles, this is our final answer here. Wow, what a process that was. There was a lot going on there, as you'll agree, but we did get the answer, didn't we? So right there, negative radical 9, there it is. I have the negative 1/9 out here, but that's the correct answer. So that would be our first case. What about the other two? So here, instead of subtracting, we're adding. So let's look at the new diagram. Now they're changing the lettering for each of these cases. Let's take a look at this one. And also the substitution is different in each case. All right, so here's the new diagram. And for this one, they want us to use u equals a tan theta. And what example do they have for us here? All right, wait a minute. What have they done here? Here it is. Here it is. No, that's not it. Wait a minute. Oh, I see what they've done. It looks like I thought they had a separate example for this one. No, they did not. They went straight on to the third case. Okay, interesting. All right. I guess we don't have an example for case two, or at least I don't see it here. What they want us to do, I guess we're going to do number three. So instead of radical a squared minus u squared, we have it reversed. Okay. And for that one, what we're going to do, first let's look at the triangle. And again, everything is a little different. And here the substitution will be u equals a secant theta. All right, but where they're sort of like they're kind of testing us in two different ways here is that they're not just asking about this integral, but they're asking us to do a definite integral, which means that we're going to have to make some changes to those limits of integration as long as we're dealing with theta instead of x. All right, so first of all, yeah, so God, they had to give us a very messy one, didn't they? Um, if you want to use this case, u is x, and that's fine, but a is radical 3 because obviously that squared equals 3. And remember, they're asking us to replace this with a secant theta. All right. So That means that x, since x equals u, x equals radical 3 secant theta. So the derivative, as it turns out, of the secant of theta is the secant times the tangent. Okay. And so we have a definition for x, we have a dx, we need something for x squared minus 3. Oh, I forgot to write that one down. X squared, it would therefore be 3 secant squared of x, a theta rather. Um, so this becomes, now there's a 3 there that we can factor out. And whenever you see something like this, your immediate suspicion should be, are we using one of the Pythagorean identities? Let's scroll up and find out. And of course we are. Secant squared theta minus 1 is tangent squared theta. So we now have all the substitutions we need. Oh, one thing we do need. Oh, yeah, we got to do something about the limits of integration because these are with respect to x. Okay. So um, x, I see what we have to do. Okay. So 2, what do we do with 2? Okay. So we remember that x is defined as radical 3 secant theta. All right. So when x equals 2, and that implies that 2 over radical 3 is the secant of theta. Now, how do we solve for this? Well, here's what you have to do. Just remember the secant is the inverse of the cosine, which means that if 2 radical 3 is the secant, that implies that the cosine rather is radical 3 over 2. And then theta is the arc cosine of radical 3 over 2. And that you can look it up directly on your calculator. Okay, so let's give that a try. Know how to do that on here. The second function of cosine is the arc cosine. Okay, so do that. Now that produces a very scary looking result on this calculator. The calculator is going to show decimal equivalents. And you might say, well, what is going on here? What is that supposed to be? But if you go in here and take a look at pi, you'll realize that that number is equivalent to pi over 6. Okay, I don't believe the calculator is capable of expressing it as pi over 6, or if it can, I've never figured out how to do that. So we're going to write this as pi over 6. Okay. The thing is, when you get a messy result like that and you're in the radians mode, you just have to try different functions of pi because it's got to be one of them. Now, when x equals radical 3, radical 3 equals radical 3 secant theta, and we can divide out both sides. And since the cosine is the inverse, in this case, it's the same thing. 1 equals cosine theta. So we try the arc cosine again, and you'll just get 0. All right, so in other words, here's what we're actually going to try to solve. Instead of this, solving it directly, we're going to make all the necessary substitutions as well as the limits of integration. So if you remember, we made several we have several definitions here. X is radical 3 secant theta. So this would be, um, and we know that x squared is 3 secant squared theta. And what does that give us? And if you look at the Pythagorean identities, secant squared theta minus 1 is, there it is, tangent squared theta. So let's do that. And that's going to simplify to radical 3 tangent theta. All right, so let's make those substitutions. And the x, as we just saw, is, and of course, don't forget the, oh, I almost forgot. Yes, where's the dx? Um, we almost missed the dx. Where is it? All right, it looks like we never defined the dx. All right, so um, if x equals radical 3 secant theta, so remember from the derivatives, the derivative of the secant of x is the secant times the tangent of x. Okay, let's quickly remind ourselves. So we have a dx now, which is um, actually d theta. Dx becomes radical 3 secant theta, tangent theta, d theta. Now, of course, there's no room here, so let me fix that up. I'll bring it down here. So we have um, radical 3 tangent theta over radical 3 secant theta. And then we have radical 3 secant theta, tan theta, d theta. All right, that should do it. Now there's some cancellation going on here. And we ultimately end up with All right, now what do we do with this? Well, there, if you look at your rules of integration for a tangent squared, you won't find it. But there is an integral for secant squared. In other words, um, let me just fix this up. There is an integral for the secant squared of x, which is, let me just check, tangent x plus c. So what we're going to do is use those old Pythagorean theorems, identities again. Let's go get one. Let's see. Way at the top, we have them all listed. And you'll see that there it is. The one we want is right here. Tangent squared theta is secant squared minus 1. That's right. All right. So here's what we're going to do. Nice. Okay. Now, this one is, of course, a much simpler because we can break it up into two simple pieces. The integral of secant theta, squared theta, is, as we just saw, where did I put it? Tangent theta. Right. Oh, you know what? I just realized we lost the radical three. Hold on one second while I fix that. There's still another radical three. So that means, yeah, let me fix that right here. All right. So the radical three can fit out here. All right. That's better. Yep. Let me just fix that. All right. Now we're getting somewhere. Okay. So the tangent of pi over 6, let me get that off my calculator, is 0.577. I think that might be radical 2 over 3, maybe? No. Um, That, oh no, maybe it's radical 3 over 3. That's one of the frustrating things about this calculator. There it is. Okay. Then we have 0. And we ultimately end up with, and so finally, after all that, now, of course, here, this becomes 3 over 3. And our final result is 1 minus radical 3 pi over 6. Ooh, wow. Boy, that was pretty tough, but we got it. It's there. Now, what they did here, now you see, it turns out that if you want to do it directly, you can, and this is what you're going to wind up with. But I don't know. I kind of like the simplification approach that we were using. I mean, if you look at that massive list of integrals that covers every case in the book, this is in here somewhere, but it's like buried in there somewhere. In fact, if you want to look back at Brightspace, which I might have open right now, hold on. Ah, maybe here it is. Here it is. This is the basic rules, but if you go back to the tables, I think I also included the full-blown version. Um, there it is, integration tables. This is the scary one. Yeah, look at this one. Let's download this real fast. Oh, it's not offering me a down. There it is. There it is. So somewhere in this mess, and you notice they're all pitched in terms of these forms. Like here are two of them that we did already. U squared plus or minus a squared. They're all in here sooner or later. But you can see that, yes, you can solve for them directly, but what a mess. I think in our cases, we were able to reduce it to something much more manageable. But there it is if you want to use it. Now, they're also reminding us about this concept of arc length we saw a little earlier. They want us to recognize that this falls into one of these three categories. Um, so here's an example. The arc length between 0, 0, and 1, 1 half. Well, we have the formula from an earlier section, but they want us to notice something very important that here's the formula, and they're making the case. Now, in this case, the function is 1 half x squared, which means, of course, that f prime of x is just x. And that is going to be squared because it's f prime of x squared. And then all of a sudden, this is just like what we've been doing. Here's our a, and here's our u. So this is a squared plus u squared, which actually, which case is that? That's the mysterious second case. Oh, see, this is why they didn't give us a separate example because they wanted to do it this way. All right, let's go revisit that one. I was a little surprised that they didn't give us an example. They must have decided to make it an application. So how does this case work? We can think of this as case two. So finally, it makes an appearance. Look at this. All right, so with that one, what does the triangle look like? It looks like the second one. Here we go. And the substitution here is u equals a tangent theta. All right. So the here we have the integral. Now, if you notice, we have a definite integral, so we have to change the limits of integration. We have 1 plus x squared under the square root sign. So a is 1, u is x. All right. So then what about the limits of integration? All right. So since x equals the tangent of theta, so we're just going to solve for the arctan of 1. And that should be easy in the calculator. Well, what a mess that is. Oh, it's pi over 4. It's hard to tell sometimes with these. It's 0.785 something. It's hard to recognize sometimes. And then anyway, when x equals 0, so theta is the arctan of 0, and that's going to be 0. Very good. All right. So what do we have? So the original question was here, right here. Let's grab that. And replace all the substitutions we made. Okay. So we've got one. Actually, we probably should have done this separately. Um, d x squared is tangent squared theta, and dx, the derivative of the tangent on the basic rules is secant squared of x. So therefore, here dx would be, wait, let me write that one more time. The derivative of tangent x. So therefore, in this case, this is secant squared theta d theta. So we're going to end up with radical 1 plus tangent squared, because that's x squared, dx is being replaced with secant squared theta d theta. Now, of course, it looks like we're looking for an opportunity to use one of the Pythagorean identities. Um, 1 plus tangent squared theta is actually secant squared theta. Well, we're taking the square root. And now that means we have, hold on one second. To make a little more space there, so you're ultimately taking the integral of, okay, so here we are with secant cubed theta. So it's kind of interesting to think what should come next. Well, it turns out this is actually a very messy case for integration by parts. Well, it would be hard to tell. I mean, it takes a lot of practice before you recognize something like this. I think they probably shouldn't have picked such a messy example right off the bat, but what they did at least to show us the correct answer, and then they went ahead and evaluated it. But this integral here is supposed to be solved with integration by parts, which, if you remember, looks like this. The integral of u dv is uv minus the integral of v du. So by going through all of that, it does end up giving us this answer down here. And then when we evaluate it, it becomes 1.148. Okay, so that is that. That's how it was done. So I think we've said enough about trig substitutions for now. I'd like to get on to 8.5, which is basically another technique for simplifying integrals, but it's very, very different. It involves polynomials. There'll be no trig functions in 8.5, that's for sure. But it enables us to take polynomials and break them up into simpler pieces and then integrate accordingly, which is what we were doing here. The difference is that here we needed the trig functions to simplify. What we're about to do does not, but we have to learn the rules that we have to follow in order to use this technique. And that technique, which is in 8.5, is known as partial fractions. Okay, so basically, we're going to take, let's say, here's an example of a partial fraction case. So you've got something that looks simple until you realize if you try to use u substitution here, you're not going to have enough information for your du. In other words, we would have needed 2x dx there, and we don't have it. And we can't supply a variable. We can only supply our own constants. So what do we do about it? That's what this next section is all about. We're going to use the technique called partial fractions. Okay, and again, keep in mind, the whole point of this is to take a messy expression and turn it into something simpler. But we have to understand exactly how that works. So this is section 5, or 8.5, I should say. Partial fractions. All right, so the first example they're going to give us is this one. Now, by the way, all of these cases that we're going to see here are, they're not going to make, I don't think there's going to be any cases where the denominator is of higher order than 2, but we'll see how that goes. In other words, mostly we'll be dealing with linear and quadratic functions. Okay, so now something like this, you might have noticed, if you look at it carefully, This can be factored into x minus 3 times x minus 2. How do you know that that's correct? Because if you multiply this out with FOIL, let's see what happens. Here's our F, O. Actually, let me move that. I need the space. All right, then I would be these two, which is minus 3x. And then last would be these two, which is positive 6. So when you combine all of that, you'll get x squared minus 5x plus 6. Okay, so what we're going to do is break this up into its two factors. So again, x squared minus 5x plus 6 is the same dx. Let's not forget the dx. Can be rewritten as this. Okay, so now the big question in your minds is how does that help? Well, this is where the partial fractions technique comes in. So this is one of the cases that we'll need to understand. Um, what they're going to have us do is this. When we have what are called non-repeated linear factors in the denominator. Now, if you notice, the two factors are x minus 2 and x minus 3. They're both clearly linear functions or linear expressions, and neither one is the same. The way we solve for this is now you're like, well, what's going on here? And now we're going to solve for A and B. All right. So we break it up into two parts, and then we find the values of A and B that make this work. So what should we do first? Let's multiply both sides by this denominator. And then we'll do the same thing on the right-hand side, of course. Now, on the left-hand side, of course, that reduces to 1. Now, on the right-hand side, you can see that for this term, the x minus 2's will drop out, and we're left with x minus 3 times a. And then for the second term, it's the x minus 3 that drops out. Oh, so we're getting somewhere now. So we rearrange these algebraically. Now we combine the like terms. And then we're going to factor out the x here. And now what do? We're going to equate the coefficients. Now, the left-hand side is the equivalent of 0x plus 1. Let's keep that in mind. So we're going to equate the coefficients, meaning that 0 equals a plus b, and 1 equals this expression. And now we're going to solve simultaneous equations. Now we've all done this before. We can use the method of substitution. What we could do, for example, is up here. This implies that minus b equals a. And then in the second equation, I can replace all the a's with minus b. And therefore 1 equals b. And based on the first equation, uh, we know that a plus b equals 0. And because b equals 1, we know that a must be negative 1. So ultimately, what that means then is that if we come back here, we can rewrite this as, remember, we decided that a is negative 1. Sorry, b is 1, not 0, 1. Okay, so now again, you're saying, well, so what? All right, all we did was prove that this expression on the left can be reduced to the one on the right. But here's where it pays for itself. Watch this. And guess what that means? You've got minus log x minus 2 plus log x minus 3 plus c. Oh my God. So that's why we go through this. All right. So just in general, if you have, and that's what we did here. Okay. So in other words, the original expression, we didn't really know what to do with it. Now all of a sudden we do. And that's our final answer. Wow, what a powerful technique this is. As you can see, it's not that difficult either, but there are several rules that we have to learn. Okay. In other words, depending on what information we have in the denominator, there are different approaches to doing this. Okay. So there's really only about 3 or 4 different rules that we have to understand before we can essentially do any case that comes along. Okay. So this was the simplest one. Again, we called this non-repeated linear factors, meaning that we have 2 linear factors or more, as the case may be, and they're all linear, but they're not the same. Okay. All right. So what are the other cases we might run into? By the way, in the slides, they went ahead and they did this with a horrendous, oh my God, look at the mess. I think the reason why they went through all this trouble, they used trig substitution from the last section, is to show you just what a nightmare this would have been if we didn't know about partial fractions. But of course, it's the same answer. And I think you'll agree, this is much more down to earth. Now, here we go. This is where they're showing you what they actually did to use partial fractions and get the same answer. So, um, let's try this one. Now, this one is a bit messier. In fact, it's a very messy one. So before we get into that, let me show you some of the other cases that you'll need to know to do these problems. So we've already seen what to do about non-repeated linear factors. What if they are repeated? All right, so let's say that we have something like this. By the way, the numerator doesn't have to be 1 for this to work. Okay, in fact, usually what they'll do to show you the general example is in the numerator, we have some polynomial or other. And, A is just some constant. So we're going to write it like this. Okay. So in other words, now A could be literally any constant, and it could be plus. But the fact that it's squared means we have to break it up into two pieces. The first one, the denominator is just x minus a. In the second case, it's x minus a squared. Okay. So yeah, maybe we can come up with a quick, simple example of this, um, just so you can see what it looks like. I'm sure they'll have their own in a few minutes, but let's see what we can do. Suppose we have something like this. So we're going to break it up. Actually, we don't really even need the integral for this. We're just the partial fractions part is not integration is what we're doing to it, but the partial fractions is just this part. Okay, so let's write it like this. Now, just like before, we're going to cross multiply by the denominator on the left. Okay, that'll be the quickest way of reducing it to something manageable so we can solve for A and B. Oh, I'm going to run out of space. I'll move this down here. Oh, wait, sorry. It's not equals, it's being multiplied. All right. And I just realized I left this off. All right. Anyway, the whole idea here is that you're going to multiply both sides, but whatever it takes to eliminate the denominator on the left. Okay. So in other words, we did this on purpose to make sure the left-hand side reduces to 3x plus 1. Okay. On the right-hand side, in the first term, we're going to have a times x minus 4. And then for the second one, we'll simply have b. Okay. So then we'll have 3x plus 1 is ax minus 4a plus b. Well, this one is particularly simple. We may not even need simultaneous equations because there's only one x. Um, that's right. That's wild. Yeah. Okay, that's true. And so again, we're equating the coefficients when we do this. So this implies that 3 equals a and 1 equals whatever this is. So we know that 3 equals a, and therefore we can plug that into the second equation. And we end up with 13 obviously equals b. So finally, when we're done, so we have 3 and 13. So we just substitute, and we're done. Now, of course, if this is an integration problem, then we carry on from there. But as far as the partial fractions are concerned, this is all we have to do. Okay. So keep in mind, this is the case of repeated linear factors. What other cases might we run into? Oh, by the way, I just want to mention here that they can be repeated as many times as we want. In other words, you may end up with something like this. So in other words, you need one term for, if the exponent is three, we need three terms, which are one, two, and three. The exponents are one, two, and three. Okay. You notice like here we had two terms and the exponents were one and two. So when we have these repeated factors, this is how it works. Okay. Now, what about nonlinear functions or factors, I should say? Now, we're going to restrict this to one special case, non-repeated quadratic factors. So if you have something like this, now keep in mind, I can't factor this, or if I do, I'm going to get imaginary solutions. So this one is, we call it irreducible. I guess that probably should belong in here too. It's understood. Otherwise, we'll break it down into something simpler. So this only works if this is something that can't be factored down any further and give us real solutions. So it becomes this. Oh, that's different. In other words, the degree of the numerator has to be one less than the denominator. Okay. And if we had repeated irreducible, that's understood, quadratic factors, what happens then? Um, let's see. Again, p over x is some polynomial. You'll have a over x squared plus 1. I'm sorry, ax plus b. And then over here, you'll have cx plus d. In the denominator, it's x squared plus 1 squared. Okay. Wow. Now, we can have any combination we want of these, and we'll see that as we go along. So these are the basic rules, but you might have more complicated cases where you have to combine different rules. Okay, that's something we're probably going to run into very often. Okay, so if you look at those, if you understand those, though, you won't have any problems. I mean, yeah, it takes a while to get used to this stuff, but these are the basic cases you might see. Okay, so these are the ones you should focus on. Just making sure I didn't leave one out. No, that's all of them. Okay, good. So let's see what they've got for us. Now, I don't know. In some cases, they might try to solve it without using partial fractions, but you'll see in every case that that approach that they're using is very messy compared to partial fractions, which are relatively straightforward. Like this one. All right, here we go. Up minus x minus 1. Now, here they're helping us out. They're saying, listen, we're going to give you a break here. We're going to tell you that this equals x minus 1, x plus 1 squared, and x squared plus 1. Oh my God, what do we do? So here is a non-repeated linear factor. Here's a repeated linear factor because it's squared. And here's a non-repeated irreducible quadratic factor. Okay, so what do we do with it? So n is some polynomial again. By the way, it's understood with these cases that these are all meant to be rational functions, which means they're ratios of polynomials. All right, so I just want to quickly review something important too. So if you have, let's say, I'll just call it R of X. And these are both polynomials. Now, if you remember, the highest exponent in an expression is the degree of that expression. So in other words, something like this is a second degree, or sometimes it's called a second order polynomial. And then you got something like this. That would be a third order or third degree polynomial. Okay, now why does that matter? Because if the degree of the numerator is strictly less than the degree of the denominator, then this is a proper rational function. Okay, well, what if it isn't? All right, well, that's a good question. Um, Otherwise, it is called improper. And why do we care? Because if it's improper, then we have to take another step. Okay. So for an improper rational function, which we haven't seen yet, what we have to do to use this technique properly, we must divide the denominator into the numerator. And what that will do is produce two terms which are proper, either constants or proper rational functions. And then we can take it from there. Okay, so if it's already if the ratio is improper, then the techniques we want to use won't work correctly. So what we have to do is first do the division, then we'll have two terms on which we can apply our techniques. So we'll see that as we go along. So I just want to mention that before we get any further, because this will show up. Okay, it'll definitely show up somewhere along the way. All right, so anyway, here's how we break this one up. And so if what they're going to do now is say, well, imagine we have some function in the numerator. Over the polynomial we just saw. And as we saw, we have all these, look at all these terms we need because there's so much going on. Let me just copy these. All right. Sometimes it lets me copy, sometimes it doesn't. Hold on one second. And based on the rules that we just went over, what we have to do is break it up like this. Now, this one is repeated. It's linear, but it's repeated. So we need b over x plus 1 and c over x plus 1 squared. So this one accounts for these two. What about this one? We'll need, oh, actually, I can fit it here. Bx. Oh, sorry, we've already got b and c. Let's use d and e over x squared plus 1. It's not repeated, but it is irreducible. That's why it has to be dx plus e and not just plain d. Okay. Now, we can take it from there. What if we knew what n of x was, we could go ahead and solve. But the important thing is we know how to do this now. We need to know how to break up one of these polynomial functions into smaller pieces. Okay. So let's see what's next. Yeah, here they're reminding you that if the rational function is not proper, then you have to divide. All right. Let's see. What do we have? Okay, so we've already actually done this one before they tried to solve for it with you know, other techniques. So we've seen this one. Let's go on to the new one. Oh, here we go. Now look at this disaster. Now, when you look at this integral, you're going to say, oh my God, what are we doing with this thing? But then we realize, oh, we can do partial fractions. Now, by the way, do not be deceived by the initial appearance. What you need to do is take a closer look. This one is irreducible. If I set that equal to 0 and solve for x, I'm going to get at least one imaginary solution. This one is not irreducible. Oh, so that was a little tricky. They want you to write it like this. All right. So in other words, Don't jump to conclusions. Make sure to take a look and see if anything can be reduced further. And then what happens then? Well, actually, let's do it first without the integral. Just so we know what we're supposed to do. So we'll have a over x. These are non-repeating linear factors. And then now this one is irreducible. So we have cx plus d over x squared plus 4. Now we can solve. We multiply both sides by this denominator. So the left-hand side is easy. So the left-hand side becomes just the numerator. What about the right-hand side, though? Well, we're going to get a lot of simplification. And so, in other words, when you do multiply this out, the x's will drop out for the a term. For the b term, the x minus 1 drops out, so you'll have x and x squared plus 4. And for the cx plus d term, you'll lose the x squared plus 4, and you'll end up with x minus 1. Okay. Now, this is going to be quite a challenge because you've got three equations and three unknowns. So I don't know if they mean for us to actually solve it, but just to understand how this works, let's take a look. If they mean for us to solve it, well, this is going to take a while. Um, but because, I mean, we could do it. Let's see what they've got. Um, so yeah, this is what we did. And okay, I guess they do mean for us to finish it up. All right, let's try that. All right. So again, the left-hand side is 2x cubed. Minus 4x minus 8. Now, here we're going to have to do a lot of multiplications. What happens when I multiply these two? Minus 4, 4x, minus x squared, x cubed. So we have, all right, what about the b term? Oh, that's easy. Bx x squared plus 4. Um, all right. And then for the C term, we actually, oh my God, Cx plus D is multiplied by x minus 1. Let's simplify this a little bit. All right. Minus dx minus cx squared plus dx squared plus cx cubed. And then what's going to happen is we're going to set those equal to these coefficients. In other words, oh no, actually we can't do that yet. We have to consolidate all of these first. But anyway, so I'll tell you what. Let's let them do all of this. I mean, otherwise we'll be here all day. This is what they wound up with. A is 2, B is 2. Looks like C is 2, D is 4, and this is the final result. So yeah, because that we had three variables, three unknowns. We could have spent an hour doing this, but that's the final result. I hope they won't overdo it like this in WebAssign, but at least you know how to set it up. And and then of course the integral that you end up with would be a lot simpler than what it would have been. You can see it mostly winds up being natural logs, although occasionally you're going to get like this last four over x squared plus 4. That would be the arctan. That's one of those really obscure ones, but it is on your chart. All right, so let's try a more basic one. This looks good. Yeah, it's sometimes they can really bring out some of the most bizarre, complicated ones. As long as you know the four basic rules that we just saw up here, you'll be fine. Okay, remember what they are. Non-repeated linear, the simplest one of them all. You just need an A, one, well, actually, you need one letter for each. If they're repeated, you need more than one. In other words, if we have x minus a squared, we need one term for x minus a and another term for x minus a squared. If we have a cube, I think I showed you down here, there it is, then you need three terms where the exponents are 1, 2, and 3. When we have the quadratic ones that are irreducible, we need the numerator to change to ax plus b. And if this one is repeated, then we need two terms just like before, one with an exponent of 1 and one with 2, but the numerators have to be cx plus d. It'll be ax plus 2, whatever. So those are your four basic cases. And we do see cases where there's a mixture of them, like we did here, but the rules don't change. You can combine them any way you like. The only thing is, remember, now they haven't shown us any of these cases yet, but if the ratio is improper, you will have to do some division first. Then you've got two simpler terms, which can then have these techniques apply to them. All right, let's look at this. Is a nice simple one. I like this one. By the way, if you notice, some of these could be solved in multiple ways. Um, well, anyway, so I mean, there's sometimes there are different techniques, and you don't necessarily have to use any particular technique unless you're doing a WebAssign problem that asks for it. But still, um, you don't really have to worry about that. So here, these are non-repeated linear factors. So you'll have a over x plus 3 plus b over x minus 3. Now you multiply both sides by the denominator on the left, okay, which you're certainly allowed to do. So on the left-hand side, we'll have 1. And of course, here there'll be a lot of simplifications. So for the A term, the x plus 3's drop out. For the B term, it's the x minus 3's that drop out. So now we rearrange this algebraically. And now gather up the like terms. Now, oh yeah, one more thing. Let's factor out the x. And then we still have over here plus minus 3a plus 3b. And now again, we're equating the coefficients. That left-hand side, 1 is equivalent to 0x plus 1. So you're setting 0 equal to a plus b because that's the x term. And then 1 is being set equal to this term. This is the constant. So what we should probably do is start with the first equation and rewrite this as a equals minus b and plug that in down here. So we'll end up with 1 equals 3b plus 3b. Okay. 1 equals 6b, which of course means that b equals 1/6. And since a and b add up to 0, that implies all right, so now we can go back and rewrite the original integral as so we had a over x plus 3 plus 1/6 x minus 3. And then we're going to integrate. So, of course, these are natural logs again. And so we end up with whoops, 1/6 natural log X minus 3. We don't need a C because this is, well, actually, I'm sorry. We do need a C. What am I saying? We do need a C. Okay, that's better. There we go. Now, it looks like what they chose to do is simplify it a little. Because, of course, if you remember, the natural log of X over Y is equal to, so that means here we can rewrite this as, and that's, yeah, that's one of the choices.